Again, Monday will be most of what you have to know by the test, right? Tuesday will be mostly review right there. So Tuesday will be kind of sort of a down day, right? So the information you have to know won't overwhelm you. And I know we have a test the day after, so I'll limit the information to one class's knowledge for Monday, right? And maybe expand a little bit on Tuesday just to review it. Okay? So, first off, just basic properties, right? Mostly when you think of kidney function, right? You're thinking of waste removal, you're getting rid of urea that's floating around the body, right? But really especially for physiology, right? Main functions here are about regulating your water balance, right? And that includes your extracellular fluid. You have a lot of fluid in here, when your blood pressure is high, right? Your kidneys are going to be able to deal with that through regulating how much water you get rid of. Like the more water in your blood, then the higher blood pressure is, right? So if your blood pressure is too high, you can pee more. If it's too low, you conserve more. Basically, right? And that's one of the things the kidney's going to do to help you with that, right? It can't create water, but it can save it to some extent, as we'll see. And the same, this is related right here. It's the regulation of osmolarity, right? The amount of solutes in the blood, and that's going to be very important all along your body tissues right there, right? And ion balance is also related to this, right? You don't need to keep the proper salt levels, right? So when you're low on salt, your body conserves more salt, right? It takes in more salt. If you have too much salt, you pee out more salt. Right? And then also related to that is going to be the regulation of pH, right? You can pee out more hydrogen ions if your blood acidity is too high or pH is too low, right? And then we only get to the excretion of waste way down over here, right? And there's also another function which we'll get into Monday a little bit, production of hormones, renin, which is an enzyme, or EPO, right? Because your kidneys going to be very involved in this whole water balance and blood pressure. And it's going to be highly related to your respiratory and your cardiovascular system. It's kind of the integrated lecture we do on Monday. So this is your general functions of your kidney. And a lot of this will make more sense. These come Monday, right? Talking about the regulation of blood pressure. But for us, even though it says 21.2, it's only because I still have my anatomy slides. Don't worry about that. When you think of kidney function, right, the easiest way to think of it is this, right? There's everybody knows that this is a dialysis machine, right? He's got an artery, whatever you want to call this, right? The thing sticking in his arm, getting blood. The blood goes through here, this tube right here, and it goes into this magic filtering machine over here. It's magic because it only takes out the stuff we want to get rid of. We want to get rid of urea, any kind of maybe stuff, drugs or whatever you ate, or medicine and stuff that you need to get rid of, right? And it wants to get back the water. It wants to get back everything else, right? So this magic membrane just removes all your undesirable elements that are in your body, and then it goes back into your body, right? That's what your kidney's doing, except it's not doing it magically, which is why if it was, then it would be done. Over here, right, the water, all the waste goes out, and then it goes inside here. This is what you're going to learn about anatomy here. That's your bladder. That's your ureters. Done right there. That's all that is. Right here, the kidney part is the important part of this whole urinary system I'm going to talk about. However, is it magic? A, no. B, yes. C, maybe. No. D, I wish. All right. So we're not really going to go. We can learn about the kidney, right? That big, clunky filtering machine is is condensed into two around fist-sized little things in the back behind your ribs. Over there, right up just below your diaphragm, right there. They're sitting there. And if we look closely at them, right? If we look really closely, we'd see, we could start to see all the smaller blood vessels, and we start to see all these tubes in there, right? And if we look closely at this, we see something like this. And this is where all our focus is, right? This is the nephron. That's going to be the actual non-magic filtering machine, right? And when you look at something like this is what your models, your kidney models, like in class look like or something like that. But in reality, there's like 1 million of these per kidney, so you couldn't actually see these. Right? So there's millions of these little guys in here. There's less of these guys over here, but there's millions of these little filtering, tiny little filtering machines, right, that are gonna remove your undesirable elements and do all that magic stuff like osmosis and osmolarity balance and all that, right? So, the anatomy of it is something we'll go over as we walk through it, right? But there's this little place where there's gonna be kind of capture the blood, make it into filtrate, and then over here that filtrate is gonna move through this whole system. Right? So just big picture stuff. Right? Here's the blood vessel going in, the blood circulates around, the blood goes out. Right? So blood goes in, blood goes out. No blood is being put inside these filters, right? What's going inside the filters is a filtrate. And this filtrate made in this little capsule right here, and that filtrate, I guess I can't use yellow. The filtrate is gonna move through these tubules right here. And then eventually it's going to be excreted. And as it moves through the tubule, right, there's a whole bunch of junk dumped off in here that we need to recapture, right? Because it's not a magic membrane, it just dumps a bunch of stuff into that tube. And we need to recapture that stuff, bring it back in the body, right? Whether it's water, whether it's essential vitamins, minerals, glucose, all that stuff. And we've got to recapture that in every single region of these tubes. And over here, we're gonna have particular properties, right, which we'll walk through. Today, not too much detail, but we're just gonna get through the general principles, right? So when you look at a picture, just draw a very simple picture for yourself to understand the flow. And one thing I wanna mention here too, about when I say inside the body, outside the body, right, secretion, absorption stuff. When we talked about the lungs, we breathed in air, and they went through your nostril, they went inside your mouth and everything, they went down your trachea, they went through a series of tubes right there, right? That was the air. The oxygen wasn't really in your body until it got all the way down into the alveoli and crossed that membrane, right? It has to cross an epithelial layer to get into your body. That's what I'll say, in your body. You might say, it's in my bronchi, it's in my body, but it's not really in your body. This is the terms we're gonna use. Until it's in your, ultimately in your blood vessels, right? It's gonna go through your interstitial fluid as it leaves the tube, right, the bronchi tubes. It's gonna go through some interstitial, but eventually it's gonna go into the blood vessels, right? And that's when I say, okay, to get it inside, it's gotta cross an epithelial boundary. When we get into the digestive system, right, we'll see this big opening from your mouth to the anus, right? When you eat a cheeseburger and stuff, it's not in your body until it crosses an epithelial boundary. It gets through all the broken down nutrients, get into your blood, then it's in your body. Okay, you've absorbed it, you've got it into your body. And the same thing, a little less intuitive here, right? But it's gonna be the same thing with the kidneys, right? You know, your urethra is an opening to the outside, right? There's a passageway to the bladder, that's not in your body. Urethra, the bladder, isn't in your body. From the bladder, you go up back toward the kidneys through the ureters, that's not in your body, right? And all those ureters, I mean the two ureters, the ureter, right, will be a collection of all these passageways, right? So this in here, right, that's eventually all this would end up in the ureter, right? You follow it back, not in your body, not in your body, not in your body, not in your body, not in your body. None of this, once it leaves these blood vessels, it's kind of outside your body. And then we're going to talk about things being absorbed from this tubule. So if we look at it from the side, so over here, and we got this is a cross section of one of these tubes, right, lined by those little tubular cells. Right there, this is the lumen. Over here, and this has the filtrate in it. And that's where the filtrate, this is outside the body right here. Okay, and then surrounding the tubule, and this is going to be the extracellular fluid, the red one. And a blood RBCs. Right? And this, extracellular fluid, this and the blood vessels, so I'll say it's leaving, it's being absorbed. And by that we mean stuff is leaving, it's going through this boundary right here, the epithelial boundary, traveling through the cell, and then leaving the cell on the extracellular fluid side. And then it's going to enter the bloodstream right there. Right, this process from the tubule, and I'll just say to the body, right? If you want me, I could write extracellular fluid, ECF, blood, right? That's the direction it's moving. And I say things, maybe we want to get rid of some stuff, right? From the blood, you got these little ions in here we want to get rid of. We're going to leave the blood vessels, the capillaries here, it's just leaving the blood vessels, going through the extracellular fluid, and then it's going to travel, it's going to pass this membrane, travel through the cell, and then be dumped into the lumen over there, right? This process over here, this one over here is called absorption. This process over here is called secretion. Right? So that's from the body, extracellular fluid, blood to the tubules, right? Those are the terms, right? We want to go inside, so this is going to be outside the body. This is the same thing. When we get to the digestive system, maybe this is the digestive tube. We're absorbing food, the digestive particles, and they're going to travel through the epithelial boundary. On one side, on the luminal side, leave on the basal side, enter the extracellular fluid into the blood vessels. Right? And this could be your capillary, your alveoli, leaving the air, oxygen leaving the alveoli through the epithelial boundary, right? In that case, the simple squamous cells passing into, diffusing through, and then getting into the blood vessel, right? All the same principle. So there's a kidney here, what we're going to be seeing, right? There's going to be a bunch of filtrate that's made, passed through a series of tubules, and then leave the tubules if we want to get rid of it, or if we want to reabsorb it. Sometimes we don't want it to go, and it'll just end up in the water, right? So this whole process of reabsorption, absorption, reabsorption mean the same thing. We're just reabsorption implies the fact that we just dumped it out. We're dumping out a bunch of stuff in that little capsule right there, right? So when you're all along right here, you want to think of this really simple process because it gets convoluted. In fact, they name those tubes the convoluted tubules, right? So, but what you want to think of is a picture like this, right? Where you got a capsule down here, you got this capsular space. That's going to move through a series of tubules, right? All these little curves have some kind of little significance over here. And I don't have to draw this, but I'm going to anyway. Right? Over here, and this whole unit right here is called a nephron, right? It's got parts to it. And over here, it's got parts to it here. It's got parts to it here, right? So this first part over here, we got blood again coming in. And blood coming out. And that's the blood. When I say it's coming out, it means that there's no blood going into the space right here, right? All that is kind of filtrate here, right? But those blood vessels are going to go along, you're going to follow along those tubules all the way. Go along here too. It's going to follow along. Why? Because this needs to happen. Right? It needs to pick up anything that is being reabsorbed and leaving the tubes from the body. Right? So those vessels are gonna be traveling along the tubes all the way, right? So this region over here, this is your Bowman's capsule, or it's called Bowman's capsule. Bowman's capsule, right? That's just the place that's receiving that filtrate over here. And then there's gonna be the tubules, right? So there's a capsule, and there's all these, the rest of it is your convoluted tubules, right? Some of them are close to the capsule. The first part, that would be called proximal, because it's close, proximal, convoluted tubule. Some of them are really far away over here, and they're connected to this part over here that's eventually going to be excreted. This is far away, so it's distal. This part is the DCT, right? This part is the tubules, that's not the capillary, this is the tubules. And then this over here where it empties is actually not part of the tubules because there's more than one nephron going into this part. This is the it's not a passive collecting duct. This is an actually very important part about water reabsorption, as we'll see on Monday. We won't talk about it today so much, but very important part of reabsorption of water. In the middle, this little loop, it's a loop. And then we can call that a nephron loop. There's another word for it, which you may see, Henle, the loop of Henle, whatever. That's anatomy. Here's just this loop over here. So those are parts of it. But again, we're gonna see big picture stuff. Right? Stuff is gonna be created in the space. Right? Filtrate's gonna be made. And this is all connected, so it's gonna be traveling through here, but it wouldn't make much sense if it was just traveling through here. Right? There's stuff going on in this filtrate over there. And we got stuff. Over here, let's call the red stuff the bad stuff. It isn't blood. Don't get confused. I just don't have any other colors to do this with. And also, the green things over here is good stuff. So we're dumping off everything in this little package right here. We're just dumping off everything. That's because it's not magic. That's the way it does, right? It's the most efficient way. And we just don't have magically permeable membranes that'll just take out the bad stuff that we don't want anymore, right? So all this stuff, good and bad, and here's the green is good stuff. I'm not sure if that's the proper word, but and then there's bad stuff. And so both, all of this, and the good stuff is going to include a lot of water, right? It's traveling through this whole system right here. So that by the end, the only thing that's left, hopefully, and a little bit of water, is going to be the bad stuff, right? Which means somewhere from here to here, right? This good stuff is being reabsorbed, right? And then brought back into the bloodstream. Okay. We'll also end up with some extra bad stuff. That doesn't mean it's extra bad, it just means it's extra than what was in the tubules. Somehow that got in the tubules right here. That will be the process, right, of secretion leaving the blood vessels right there. Right? We're gonna dump some more stuff, we're peeing stuff out, why not get rid of some stuff on the way? Right? So you can leave stuff out there. You can dump stuff out that'll be excreted in the urine. But that's the basic big picture of what we want to do, right? We'll look a little bit into the mechanisms of how we do it. Right?
Does the reabsorption happen in the DCT?
The reabsorption is happening the whole way through. You know, we'll talk about major areas of where it might be happening here, there. But absorption and secretion is happening the whole way through, right? So the capillaries are going to be picking up stuff, dumping stuff off the whole way through. We'll paint a more simplified picture where the main reabsorption is happening in the proximal convoluted tubule, secretion maybe is happening in the distal, concentration and all that. But we're actually looking at a very simple picture today, right? As far as we'll get in a little more detail about the details about where it happens and stuff like that. But in general, right, your nephron function is going to be all that stuff right here, right? So we got Are we good here? Right, secretion, just have to make a little room. You always wanna remember these terms here. Filtration, and again, right, this is just leaving the blood, this is plasma, this is not blood, this is not a lot of things, it's just a filtration, you're making a filtrate, right? The kidneys, that Bowman's capsule is where we're gonna actually make a filtrate, right? So we'll leave the blood, and it's gonna go into the lumen, we're gonna start that out of the body experience into that Bowman's capsule, right? And then the second function, sometimes I call it absorption, it's technically reabsorption because we just dump it out there. Same process. I don't know if there's anything special about calling one or the other, right? But you're from the filtrate back into the blood right there, right? That's reabsorption. What's the other process? Exactly, secretion, right? There's another thing, we can get rid of extra stuff. We can get stuff from the blood vessel, dump it out into the lumen, and then we're gonna pee it out. Right? So that's secretion. Secretion is not excretion. Secretion is just leaving the blood. This is a very particular process of stuff that's leaving the blood, going through the extracellular fluid, passing through these membranes, and being secreted from the blood into the lumen, right? Of the tubule. The last part is actually excretion, that's different, right? You're leaving, ultimately, this is what's gonna be connected, eventually dump into what'll become the ureters, which is gonna go into the bladder, which is what you'll pee out right there, right? So there's a process, it's not just stuff, you're not just getting rid of the good stuff, bad stuff immediately. Right? We have to do this whole process because, again, it's not a magical thing, right? It's just a product of biology that happens like this, right? All right, so dumb questions like this. From the blood and adds them to the filtrate. So it wouldn't be filtration because we're adding it to the filtration. Selectively, the process of filtration is like a mass dumping, right? So that's not selective really. It's a little bit selective, but not quite.
Reabsorption?
Adds them to the filtrate. We're going from here to here. From the body to the tubule.
Secretion.
Yeah, secretion. That's that, right? Just get these turned down, draw a picture of yourself like this, and just draw a cross picture. This is the lumen of the tubules, and outside of those tubules is the body. Right? So we're moving stuff in between. If it's going from here to here, that's reabsorption. If we're going from here to here, that's secretion. Right? And then final thing is over here when we're peeing it out, right? Excreting it. Eventually the stuff that ends up in the bladder. Right? D. Right. So you got a lot of stuff going through here, right? A lot of stuff that we have to be absorbed. The numbers here, right? The stuff that's being dumped into this little Bowman's capsule, this process is being filtered. Your blood circulates through the liver, through the kidney, about, let's say 180 liters a day of blood is passing through these right here. Okay, it's passing through 100 liters a day. And then that filtrate that's made 180 liters a day right there is the same osmolarity as the blood right there. It's gonna be the same because it's just plasma. That's being basically it's plasma, it's not everything. But there's about 180 liters a day, right? If you kind of do the calculations on that, you can see that your blood is 6 liters a day, right? What is your 5 liters of blood you got? How much of it is red blood cells? How much is plasma, right? You'd end up with something like 3 liters of plasma, right? Every minute or something like that, every hour. One of those numbers. Anyway, you do 180 liters a day, that's what you're kind of gonna filter right there. Do you pee out 180 liters a day? You know how much 180 liters a day? It's a lot, right? Maybe the size of, I don't know, more space, but say it's the size of this blackboard. But you're not peeing that out, obviously, which means you're doing a lot of, oh, I forgot to do this right here. Numbers. I had some tricks there. Right. But by the time you get over here to this so-called loop of Henle right here, the nephron loop right here, you've gone from 180, right? This is processing 54 liters a day, which means we lost 180 minus 54. What does that mean? Where did all that go? Right here to here? Reabsorption, right? Most of it was reabsorbed pretty immediately, right, in the first part of this proximal convoluted tubule, right? So 70% of it has already been reabsorbed by the time it gets to this loop right here. So you're doing 54 liters a day, about 30% of volume. It's still, at this point, the same osmolarity, right? That means that we are keeping the same concentration, right? There's gonna be a process here that we'll talk about Monday a little bit, as it goes deep down into a very salty area, and water's gonna leave, and we're gonna pump out a bunch of ions and stuff. Ultimately, we'll pump out a bunch more ions, so that by the time we get through over here, why did I do this? By the time it gets here, it went from 54 to 180 liters a day are passing through this region, which again means what? We reabsorb a lot of stuff in this nephron loop right there, right? Also notice the osmolarity went down, which means we took back a lot of the salts, all of those solutes in there, we removed most of those solutes, right? So it's very dilute at this point, because we pumped back. This area was concentrated, reabsorbing most of the water, but then we're gonna actively pump out all those ions and get them back such that this point over here, it's very dilute. That's what we want. We don't want to pee out all our precious minerals and ions and all their solutes in your body right there, right? And then by the time it gets through here, over here, by the time it gets to the end of the collective duct, it could only be about 1.5 liters a day, which is about more likely what you might pee out a day at this point, right there. And so you can do the calculations on this, and you'd end up something like all that filter that goes there, you're only peeing out about 1% of what you're filtering through. That's this process, and just to give you an idea how much is being dumped out and reabsorbed right there. Right? I don't want to ask particular numbers or anything, I'm just trying to get you the big picture here of how much we're doing, right? So we have a process here, right? Things are being filtered, right? A whole bunch of stuff is being dumped out. And then a whole bunch of stuff, as it moves through the tubule, is being reabsorbed. And there's some stuff secreted over here, right? So there's gonna be a certain volume out here. So how would you calculate the amount excreted? What would be your numbers? Think about that for a second. What are we gonna start off with? Filtered. And then what?
Reabsorption.
Is that gonna be plus or minus? Minus. We'll say R. And then we're also secretion, is that gonna be a plus or a plus? And that'll be your excretion, right? That's what that excretion is. So this will be a big number, right? This will be a small number, this might be a tiny number, whatever, but that'll be what you pee out there, right? So amount filtered, plus amount reabsorbed, plus the amount secreted is gonna be what you actually excrete. Right, so that's a big picture, and that's what we moved through all the entire tubule already, and so we're done. Except that now we got enough details of this reabsorption stuff. Not too much detail, right, but some details. Okay. So we're gonna walk through filtration a little bit, some of the stuff that's important about filtration, and then we'll talk about reabsorption, various secretion. I'll just say a sentence or two. We're not gonna get into details about secretion. Just some of the, or excretion really. We'll talk about that for a second, right? So the first part, talk about filtration. This is happening in that Bowman's capsule. Again, blood is coming in, blood is going out. Okay, filtrate's being made in this little capsule. Okay, so it's a fluid-filled capsule. This is a capillary network called Bowman, the glomerulus. Over here it has a special filter, membranes and stuff. We're not gonna talk about any of that either, except to know that this is very porous. A lot of stuff can come out of it. And that's what you want, right? You got a lot of pressure going in, just like any capillary, and stuff is leaving it, right? That's what we talked about with capillary action, right? Moving stuff out of the capillary. But in this case, very porous. All those little holes, a lot of stuff going through. Not everything. A red blood cell, remember this is a capillary. Red blood cell is about this big. There's no red blood cells coming out of here. If there is, if you have pee in your urine and it's coming from this, there's a problem, right? That means this has been broken down at some point. You shouldn't have that. Also, proteins are usually too big to get through there also. So mostly what's coming through here is the dissolved part, the stuff that's dissolved actually in the water, in the fluid, the plasma that's coming out. So mostly the plasma. Proteins, some proteins can't make it out, but also there is actually negatively charged glycoproteins. Again, I'm not going to talk about that, but there's a reason why proteins aren't leaving here, besides the size right there. But ultimately, mostly, all your plasma and the dissolved solutes in it are coming out as filtrate. What are those dissolved things? Sodium. Do we like sodium?
Yeah.
Unless we ate too much sodium, we like sodium. We want to reabsorb that. Chloride, obviously, if it's going to be the same kind of balance there. Potassium is going to be in there. Anything else? Glucose, big one. Do we want to recapture that glucose?
No, but your body does.
Your body does, you know, your body does. Maybe you do. Evolutionary speaking, though, glucose wasn't that easy to come by, right? Your body's gonna work very hard at absorbing your glucose in your intestines and keeping every little last drop of it, every much of it could, right there. So you don't lose that glucose that you worked so darn hard for. You climbed a tree, you had to fight other monkeys, right? And you need to keep every little bit of it, right? So your body's gonna be working very hard reabsorbing your glucose back there, right? But it's dumped back in there just like everything else, because it's dissolved, right? Other things are minerals, vitamins and stuff like that, right? And also the bad stuff, urea, mostly that we wanna get rid of, maybe some toxins and stuff like that we wanna get rid of, but everything is dumped off in that filtrate right there. And then from here, this is the capillaries here. We're not even gonna talk about those cells in there or anything like that. We're just skipping right through that saying, this is what you gotta know right there. And this filtrate is then gonna enter that proximal convoluted tubule right there to start this journey through, right, through the whole tubule system, out the collecting ducts to maybe become urine or maybe not. And so this process over here, stuff is going to be moving in, so the so-called afferent bringing in arteriole, that's controlling the blood flow into this capillary network. Again, it's called the glomerulus. So blood is going to go in, and it's going to go out. It's not going to go out through a vein as normal. It's going to go out through another arteriole, right? Which is kind of weird, right? Yeah. It's going from an artery to an artery, because it's not really a typical capillary thing like we might see. Right? But that's important when you look at the difference between arteries and veins. Why this is an arteriole. So all the rules that you learned about and forgot already about blood moving through a capillary network, that is, what was the driving force that made blood, or rather filtrate, come out of the blood vessels? Hydrostatic pressure. Exactly. Somebody, well, it says it out there also. Hydrostatic pressure is going to be forcing, and it creates a pressure, and because it's very porous, a lot of it is coming out, right? So it comes out in around certain, I'm not going to ask you the actual numbers here, I just want to get the basic process. A lot of filtrate is being pushed through that hydrostatic pressure, 55 millimeters per mercury of pressure is being forcing that out. However, that isn't the ultimate pressure leaving it. Right there, the amount of the net filtrate pressure is going to be balanced by other things opposing it. These two purple ones are stuff that's opposing it. Anybody remember anything about capillaries? What might be opposing? What would cause absorption? Osmotic pressure. Osmotic pressure, that's that little pie thing right there. And there's more really, a little more osmotic pressure right there, right? That's the sucking force, remember? So that's gonna drive stuff in. That was what caused reabsorption in our normal capillaries here. We don't want that, but luckily, this is greater than that, so the ultimate flow is gonna be out, right? That makes sense, right? And then the other thing opposing it, and that wasn't really a big factor in our capillaries here, was this is a fluid-filled space here, and there's hydrostatic pressure in this forcing stuff back in as well. Right? But if you add these up, 55 minus 30, it's just gotta calculate. Anyway, you do these two through the 45, 55 minus 45 is equal to, so you don't even need a calculator. But ultimately, that means that's the net filtration. There's a net stuff of stuff leaving out, which was what you'd expect right there. But that's what these two things right here are opposing that flow, but it's not enough to overcome this pressure right here. But the reason I'm saying these two things is sometimes you don't have enough pressure going in, right? Or we want to increase the pressure, right? And then those things can tip the balance a little bit, increase filtration or decrease filtration, right? And so you think, well, this 55 mgs is coming from your blood pressure, your mean arterial pressure. It's going to depend on that, right? If blood is flowing in here, if you have a high pressure right here, maybe this will be a little higher, right? But as it turns out, it's usually very steady, no matter what your blood pressure is. Okay, don't worry about this graph too much. Filtration rate, here how much blood is entering those capillaries, the glomerulus, right? This first looks like it's dependent on the arterial pressure. If arterial pressure is low, filtration low, right? And it starts to go up on a linear curve, right? But at normal blood pressure, this is your normal, roughly mean arterial blood pressure, right? It kind of evens out at 180. Your glomerular filtration rate, how much is filtered, is going to even out at 180. Notice from a range of blood pressures from here to here, you're still doing 180. That is, if your blood pressure raises a lot, your glomerular filtration rate doesn't raise until you get way over here. So it's a very steady glomerular filtration rate. Right? The glomerular filtration rate, that's how much blood is moving through those glomerulocapsules and filtrate being made. That 55 millimeters per mercury is very steady. And ultimately you're going to filter 180 liters a day. Your blood pressure is high, your blood pressure is low. In other words, in this range at least, right, in kind of normal, like, this is like you're hemorrhaging or something like that here, right? You're very low blood pressure. Here, there's like, you're doing a lot of stuff and it's going to increase. But on a normal everyday activity, the blood being filtrated is basically the same. Whether you're very active or very inactive, right? There's something that modulates it so that it doesn't depend on your mean arterial pressure within those ranges. You're filtering the same amount of blood, right? How does that happen, you're wondering yourself? I'm gonna tell you, don't worry. So blood, right? When blood is coming in right there, the pressure going in, right, would be the same right here, but we can change that. We can change the amount of flow simply because these are arterioles. What do we do with arterioles when we want to decrease the blood flow to a tissue? And we go from this, we squeeze it, right? And what that's going to do is decrease the flow to this, right? So if your blood pressure is too high, all we got to do is shut down the input, right, by squeezing the afferent arteriole. Okay, so it's going to automatically do that. I'm actually not going to discuss how it's going to do that, but there's a little bit of the muscle cells in there can detect pressure. There's other cells around here that detect pressure, and it's going to modify it. So it wants to have a steady. So this increased arterial pressure would normally increase the amount of blood flowing through there, but if you restrict it, right, then you can decrease the blood flow to match that until you only have 180 liters per day. Basically, your glomerular filtration rate is going to be the same. What if your blood pressure is too low? Well, this is where this is not a vein, it's an arteriole comes into play. This is an arteriole, we can restrict blood flow leaving here, right? So when you restrict blood flow, that's going to restrict blood flow here, but what does it do behind the constriction? Exactly. It builds up blood pressure behind here, that's gonna increase the blood flow out of there, right? So that is how we control the glomerular filtration. We just adjust the blood flow either entering, right, based on this, if it's too high right here, entering, sorry, over here, right, we just divert the blood flow somewhere else and it doesn't go here, and we keep a steady pressure. If your blood pressure is too low for whatever reason, we could dilate this, but they're pretty dilated to begin with, so what we can do is just back it up a little bit, cause backup pressure behind it by squeezing those efferent arterioles. Does that make sense? Could it make sense if you thought about it for a little while, even if you don't immediately? Are you gonna forget it in 5 minutes?
Yeah.
Okay. But if you could understand it for a second now, just kind of go over a little bit. And that's the base, that's your glomerular filtration. That's the glomerulus. So, we're talking about filtration. Which one of these would oppose it? This is all basic, like when we talked about the capillaries before, it's the same kind of stuff, right? Except that maybe that fluid pressure in the Bowman's capsule was a little stronger, it was an enclosed capsule, a lot of fluid rather than the interstitial space. So the fluid pressure in the Bowman's capsule would sort of tend to make the blood push into the capillaries, right? And it does, a little bit, but it's not as strong as the capillary hydrostatic pressure. This is what drives it. These two, right, if there's colloid, just like the colloid pressure in your capillaries promoting absorption, right? We're opposing filtration, right? So these are the same principles as blood flow through any capillary, right? Except that ultimately we're just, the whole way through, we're pushing out stuff. Okay, so this is filtration. Any questions on filtration?
So it's mainly B,
No, the things that oppose filtration are gonna be A and C right here. Those are gonna be the things that oppose filtration, right? These things would promote absorption, like in a normal capillary, right? Remember, this is the main thing that's promoting absorption in a normal capillary, the osmotic pressure, right over there, because you're drawing water in. That's what we don't wanna do in this, or not so much, right? In this, we don't want this to overcome this, which we do in a normal capillary, but here we're interested in filtration. Over here, this would be something that's also opposing it. That would be hydrostatic pressure forcing from outside to inside that blood vessel, capillary. So this would be the main thing promoting filtration. These would be the things opposing it. Okay, and then we could change the capillary hydrostatic pressure by increasing the blood flow or decreasing the blood flow over there, right, through those arterioles. How are we increasing it? How would we increase the hydrostatic pressure of the capillaries?
Increase blood flow?
That would be one way.
increase resistance.
What else can we do on the other end? That's not a vein, it's an efferent arteriole, right? When we squeeze off that,
So raise of constriction?
right? Just over here, when we squeeze off this, that's gonna create pressure behind there, right? So there's two ways we can increase it, right? So if we want to decrease the glomerulus, we can constrict it here. That would decrease the blood flow through here. If we want to increase the pressure, right? We just squeeze over here and that creates a backflow, right? So we made the filtrate now. We're good with that. We made the filtrate over here. Now it's gonna pass through these series of tubules, right? And things are gonna leave the tubules, all that good stuff that we wanna get back, the water, glucose, the ions. We're gonna get it back, we're gonna put it back in our body. Because we just dumped it off because we don't know how to do it otherwise, right? Maybe that's the best way, but that's what we do, right? So this secretion, the reabsorption part is the topic of the next part. And for here, maybe we want to think of how do we get things from one side of aluminum to the other, and what this brings us back to the first or second meeting, way back when, sometime in June, when we talked about membrane transport stuff. Right? So we gotta get from one side of the cell to the other. We gotta get from the luminal side to the basal side and into the interstitial fluid. And this is all reabsorption. And guess what? Reabsorption is all driven by, we talked about those membrane transport stuff, remember? Everything was dry, remember everything's gonna move down there gradient. If they can pass through the membrane, they're gonna move too, right, based on their concentration gradient. Sodium, it's part of the blood, it has the same blood, has the same osmolarity, right, the same concentrations of sodium chloride as does your extracellular fluid, right? And the cells are different, right? So sodium's always gonna be driven inside the cell, right? And it's gotta be actively pumped out the other side to an area of higher concentration. Right? But the first part of it is you're reabsorbing. Your book is talking about active transport, but doesn't explain what that means immediately, but we're just gonna assume that sodium is leaving the filtrate into the cells, into the extracellular fluid right there. Right? So it's gonna be moving through here. Sodium is your main driver of all these, because we're gonna use sodium to couple it with other things, right? So, first part, right? Whoops, over here is that sodium is reabsorbed, and it goes from lumen to the extracellular fluid and eventually into the blood, right? So there's a lot of sodium here, a lot of sodium here. Of course, this side is gonna be pumped out by the ATPase pump right there, because it's moving from an area of low rather to high concentration. Okay. Here, it can be moving either way. Don't worry about it. We're just gonna say it's gonna be moving from here to here, where the cells are gonna let it through. Very easy, right? When sodium is pumped here, you create this electrochemical gradient. All those positive ions over here, that creates a negative charge here. What happens when there's an excess negative charge over here? Chloride, any anions, like maybe bicarbonate ion, wants to get and join that. Right? They're going to be attracted. It's going to flow down an electrochemical gradient. Sometimes it goes through the cells, sometimes it goes through the cells. Paracellular transfusion. So that sodium, salt, all the chloride's gonna follow. What happens when you have a lot of salt on one side?
Water falls.
What's that?
ATP.
ATP is, maybe driving some of this, but maybe the pump out here. But what happens when you have a lot of salt here, more salt here than here? What follows?
Water.
Water is gonna follow, right? And that's how we absorb the water, right? We're pumping out all that sodium chloride. Water is gonna move by osmosis, right? Either through the cell or through the cell, right? We're basically gonna do that whole process of osmosis, where water follows the salt. And that's mainly the main way we actually reabsorb water on any one of these fields, right? We're gonna have a higher concentration of salt out here, and water is gonna follow. Right? And we just could change the permeability of the water channels or something like that, as we'll see later, to kind of change that absorption. But this is how we get reabsorbed water, right? We just create this osmosis gradient, osmotic pressure over here, where the water is going to be absorbed through there. Okay, make sense? Sure it does. And then the rest of them, right now, when you do that, you're concentrating the solute a little bit, so that you get a high concentration of things like potassium and calcium, urea and stuff. They're going to be moving toward that, away from that concentrated area over here as well. So all these kind of things we want to get through, they're going to be transported one way or another that we're not particularly concerned about, but they're going to move through and get back in there. That's how we reabsorb stuff, right? Salt, then chloride, there's the salt, sodium, then chloride. We have salt, now water's going to follow the salt, make it more concentrated, and all these other ones are going to flow through here. Okay, that's how we're getting most of your products right now. That's like the easy kind of picture of reabsorption. And then if we look at the pressure going into here, and there's a pressure exerted on the tubules just like there is in blood vessels over here. And there's also pressure over here. And ultimately, pressure over here that's built up is going to favor reabsorption into the bloodstream right here. Right? This pressure gradient. Right? There's gonna be more pressure over here, either the hydrostatic pressure, or the osmotic gradient is gonna make blood, all that filtrate that we just reabsorbed go into the peritubular capillaries that are following along. Okay. Okay, so that's your basic picture of reabsorption. Here, I want to just talk a little detail here about a particular type that's very important to us and then to many diseases, or one of the biggest diseases, the biggest conditions right here is this glucose production. We've actually already covered this a couple times. If you remembered everything I ever said, then this will all be reviewed. Right, but basically, you got glucose, right? It's considered low compared to the cell. Your glucose levels are pretty high in the cell because your cells, these are active cells, right? Look at all this cell membrane stuff, right? That takes a lot of energy. They're using a lot of glucose. Glucose is very high in these cells. Glucose relative here, depending on how much sugar you're eating, is fairly low. But we want to get it from low to high concentration, right? We're going to do it through these transporters. And we're going to use the sodium gradient, as we talked about, to transport glucose in. This SGLT is a sodium glucate transporter. And it's going to couple the natural concentration gradient of sodium to bring glucose against its gradient. Okay, so that's secondary active transport stuff. And we got the sodium through the sodium potassium pump over here, right? That's how we got that gradient. And then we're going to move it through, but we're going to move that glucose in, right? The thing about the glucose transporters is, now thinking way back again to this whole unit, is that these are limited, right? You can only do so much. They're going to become saturated, as we'll see. But they're going to do as much as they can in normal glucose spilling out levels. They're going to be able to reabsorb all the glucose. Once the glucose in the cell, you're going to have high glucose, but the cell doesn't deserve it all, even though it's working hard to do it all. The body wants to get it back, so it's going to leave the cell into the extracellular space down its concentration gradient. Okay, on the other side, this is the glucose, your normal glucose transporter. Okay, so these secondary active transport on this side, when we're moving from low to high, are going to be on the luminal side, located, right? That's why the membrane transport channels are located. And then these high to low, these normal diffusion, these are just facilitated diffusion, is going to be located on the basal side, going into the interstitial fluid, and eventually the blood vessels. Any of this seem familiar? Anyone besides someone? Right? So you can kind of guess all this. This is just transport. We're just moving things. Oh, here, we need to reabsorb the glucose. So the sodium gradient is helping that. It's going to be coupled. The glucose transport is going to be coupled at the SYMPORT, right? Secondary active transport. Glucose moving in the cell, right? Against its gradient. Once inside the cell, it can flow from high to low just through normal transporters, normal facilitated diffusion. Basolateral side, glucose is just flowing from here, and there's going to be a pressure difference, the concentration difference between here and here. It's going to eventually get into the blood cells as well. But all this, again, is driven by that ATP pump, where you have that sodium potassium pump pumping sodium out against its gradient to maintain this high to low gradient. So we always want sodium moving to the cell, and we're going to use that to drive all that other stuff. Okay? Now, here's the thing about this. That makes sense. I know it does. It could make sense. Could it ever, did anybody say, that could never make sense to me? Right, that's all repeat. I've already gone over that. I know we forgot it, but it should be kind of a little bit of review. The thing about transporters there's some properties about transporters and enzymes and stuff and proteins. They can't handle everything, right? There's a certain point where they're overworked, they just can't handle the load right here. That's saturation, right? They reach their maximum rate of transport. And so far, there's a certain level they can transport everything, all the glucose in your blood, but at a certain level, they can't do it. So if you're having a lot of high blood glucose for whatever reason, and this would indicate diabetes, right, having high blood glucose, whatever, in your blood, it's not being taken up by your cells, now it's in your urine. And in fact, does anybody know what diabetes mellitus means?
Mhm.
Sweet urine.
Yeah.
Back in the day, to test for diabetes, right, they had, guess who, not the doctor, test the urine for taste, but students or the nurses. They taste the urine and say, this tastes a little sweet. That means there's glucose in it, right? That means you're peeing a lot of glucose out. You shouldn't do that, right? Your body is trying to conserve it. That means you got too much glucose in your blood, basically. Okay? That's what all that means. So I'm gonna show you a couple of graphs here, right? Don't freak out. This is the filtration rate of glucose. Basically, everything is coming out of your, into the filtrate right there. Everything, glucose is just indiscriminately coming out. You can filtrate as much as coming out. The filtration isn't gonna be effective. If you have a really high level of glucose, you're gonna have a really high level of glucose in your filter. So this is a linear graph, right, showing the filtration rate. It doesn't matter if you're 100, 500, right? It's gonna filtrate everything. And it's gonna push as much in that system as it can. It doesn't know any better, right? And then the reabsorption is gonna follow along with that, right? So if you have zero, right, there's no filtration. As it raises, you absorb more and more and more as your glucose levels, your glucose levels rise, right? Your reabsorption rate will rise because your transport ones are gonna be acting as much as they can right here until it gets to a certain point, right? And at this point over here, you would still keep filtering stuff forever, but at a certain point over here, your something's gonna stop right there. Those transport around here, when your blood reaches about 300 levels or so, right? Over here, at that point, you're not gonna be able to transport. That's the max you can transport, right, as far as the rate goes, right? So you were reabsorbing it, but if your glucose levels are too high, if they reach about 300, remember your normal range is here. If you have your 300 mgs per 100 mils, you're diabetic, basically. You have a lot of glucose, right, in your blood. Way too much for your transporters to handle. So it maxes out somewhere around there. And then ultimately, over here, it kind of steadies out. And if you kept on getting more glucose, you'd just be peeing out more glucose. Okay, you'd just be peeing out past that point right there. So your reabsorption rate of glucose maxes out about 375. Anything above that just gets peed out. And that's what this chart means right here. Okay. That makes sense? Sure does. But then, so in other words, your excretion, if you looked at how sweet your urine is, and this is the plasma glucose over here, and this is how much is excreted ultimately, right, after that renal threshold is met right there. So if your glucose level is above that, this is your excretion rate right here. It goes up after that point, you're peeing out more and more and more glucose. Right? And that would just indicate when you get a urinalysis test, and they test your level of glucose right there, they can get an idea how much you're excreting. That'll indicate how much is in your blood. Right? If you're excreting urine, it's above 300, right? Way above that normal range right there. Okay, so you combine all these charts. This is what I think I gave you, right? The filtration rate, you keep on, you filtrate as much as you got right there. You reabsorb as much as you can up until a certain rate where those transporters max out. Right? They just can't handle anymore. And at that point, no matter how much more glucose, it's just peed out. It's not reabsorbed, it's peed out in the blood. Okay? This is the amount excreted. This is slide 30 of 33. Okay.
What's the graphs?
All right, so that is reabsorption, right? With a little special attention to glucose, right? It's common, something we want to pay attention to, right? So the last part of it, I'm not going to talk. You could look at the pictures, the very complicated pictures of secretion and all the channels, but we're not going to talk about that. We just want to know that secretion is important because you're removing stuff, toxins. Right? Anything that's in your body that we want to get rid of, maybe excess hydrogen ions, stuff like that, excess anions. If you're taking certain types of drugs and stuff, or medicines, right? The things that you ingested, right? We can get rid of them right here, right? And so you're gonna move those out, dump them in the tubules, and then pee them out right there, right? And then it's a very active process. In other words, that's the 2 important points. You gotta use a lot of energy to pump those out in there. And that's all you gotta know about secretion, right? Which is something I cut out a lot of details about how this happens. That's all you wanna know. You're moving stuff from the blood vessels into the tubules, right? And that takes a lot of energy. Just stuff we wanna get rid of, right? So, almost done here. Now, we've made it. We're gonna talk more on Monday about like extra absorption stuff, how we control like the amount of fluid, all through the system right here. But now we're gonna assume that what's coming out here, we're gonna pee out, right? So it's gonna leave these tubules, and it's gonna go into more and more larger tubules until it enters the end of the kidney, the renal pelvis, goes out down the ureters, and then enters the bladder. Okay. This is your bladder, this is a relaxed bladder. This is when you don't have so much pee in it right here. It's a bag, basically a muscular bag right there. And then it stays in the bladder and not out through the urethra to the opening right there, because there's a little sphincter right there, a little closing up the smooth muscle right there. Over here, that keeps it naturally kind of, there's a tenseness to it that keeps it closed, so you're not constantly dribbling out urine, hopefully. At a certain age, it's not constant, there's a natural tone to that, right? Also, you have another sphincter, a second sphincter. That's the external sphincter. This is skeletal muscle. Remember anything about that? This is under voluntary control. However, there's normal muscle tone. That's gonna keep that closed from the ages of, say, 2, if you're toilet trained by then, so you get about 85 or 90. Things start dropping out without you thinking about it. In any case, these are 2 passageways that we can control urine from here to here. And so we got this constant, the motor neurons going down, keeping this contracted right here. Tonic discharge, keeping some tone over here so you're not dribbling out urine. And this is controlled. Higher CNS, this is skeletal muscle, this is your big brain. It's saying, don't pee now. You can't pee right there. Don't do that. Until you're this close to the bathroom, and you get closer and closer. And for some reason, so in any case, in normal things, what happens is your bladder stretches, and right, at that point, this is called the reflex, right? The micturition reflex. Your receptors fire because there's stretch receptors in here. Sensory neurons again pick that detection up, sends into the spinal cord, and then your spinal cord decides what it wants to do with it at any given moment. Right? So what happens is that sensory neuron is actually connected to 2 neurons. One of them, which is exciting, the parasympathetic, which would basically stop firing over here and relax it, right? And cause this flow right here, right? Motor neurons over here. On the other hand, this one over here, right, this is going to stop this from contracting, and that's going to loosen up the skeletal muscle. Right? That would normally, when your bladder's filled, basically it wants to void. But this is like a baby reflex. This is an infant thing, and we have control over this, right? So there's higher centers over here that's going to inhibit that entire reflex of automatically peeing every time your bladder stretches. Right? So basically, all this can avoid, right? We can override this sort of reflex. Right? Again, we just developed that muscle tone that inhibits that. So basically, that's micturition, and how we control it is through these pathways. All right. Any questions? That's the basic big picture of the kidneys, right? The whole function of absorption, filtration, absorption, secretion. A little bit about micturition. And next time we're going to go into a little more detail about water balance, osmolarity stuff. We'll go back to the kidneys and also its interface with your cardiovascular and your respiratory system. So